Hello, everyone, and thank you for joining us. We know that you are very busy, and we appreciate you choosing to spend the next 45 to 60 minutes with us. We have a very special webinar ahead, and I hope you find the time that you spend with us to be informative and interesting. Victor. Next slide, Victor. My name is David Ronald. I'm Director of Product Marketing here at Tigergraph, and I'll be your host for today. Next slide. And I'm very excited to introduce our speakers, our presenters. We have Tony Baer, who many consider to be a data warehousing guru, and I would certainly count myself amongst that group. Tony is the founding principal at DB Insight, a consultancy committed to providing an independent view on the database and analytics technology ecosystem. Tony has a very rich and lengthy background in consulting and is very well qualified to speak on the topic of data warehousing. He is prior to starting DB Insight, he was principal analyst at Ovum for over a decade. He was an associate analyst at ZapThink. He was a principal on strategies, again, for over a decade, and he was an analyst at Data Monitor. So as I mentioned, a long and illustrious background. And he has a bachelor's in communications from the Annenberg School of Communications, a very well-known school. And we're joined also by Victor Mui, who has many years of experience across a wide variety of fields: databases, graphs, analytics, SQL, data warehousing, machine learning, cybersecurity, enterprise search. He's been at Tigergraph for almost 2 years, and he's an all-round great guy. So welcome both Tony and Victor. Next slide. And before we get into the presentation proper, just a few housekeeping issues. Everyone's phone is muted. That's standard these days, but that is not a sign that we don't want to hear from you. We absolutely do. So please, at any time, submit your questions. You can do that using the Q&A tab. The chat tab also works, but best is the Q&A tab. The webinar is being recorded and will be uploaded to our website shortly. The URL is shown there. And that typically happens within 2 to 3 hours. Additionally, we will send an email to everyone, and that will include the link to the archive. So you don't need to make a note of that URL shown there. We will send you an email, and you can just simply click on that URL to access today's archive. And in addition to that URL, in the email, we'll provide we'll provide other materials that may be helpful to you that Tony and or Victor feel they want to share. And last but not least, if you have any issues with Zoom, please contact us, and we'll do our very best to resolve those issues as quickly as possible. So with that, I'd like to turn the webinar over to Tony.
Okay, thank you, David, and thank you everybody for taking time out of your day. Spend some time with us in this discussion. What we're really looking at in this in the next hour is really it's really a story of the evolution of analytics. And I remember being back in this field. I dye my hair gray, but I do have the tire tracks on my forehead to prove I've been here. Back at basically the dawn of data warehousing, we're talking about like a little over 20 years ago. It was in the run-up to Y2K. It was during the period where we were re-architecting our enterprise systems. We were putting them out on relational databases and getting real access to data. It's also when it was the era when basically we started to see a lot of rich desktop clients. So getting beyond green screen reports, it stirred a lot of imaginations. And the rallying cry was get data out of the data jailhouses into those data warehouses. So we're going to kind of go through, to trace this narrative, and the narrative we're going to talk about today is how analytics has really evolved, and essentially it's really the story about how graph analytics really complement, they don't replace, but they really complement your the analytics that you've been relying on. Later on in the session, I'll be joined by colleague from Tiger, Victor, who will be going doing a deep dive into basically how you use this, the use cases, and we'll show some pretty demos. David and I had a chance to get a peek of these, and I hope we have enough time to get through all of them. They're really quite fascinating. Can we go to the next slide? So anyway, this is kind of where we all started. I was kind of alluding to this, in the opening, which is that data warehouses, emerged because of the nature of analytic queries. They're a lot different from the process of processing, transactions, and it caused a lot of basically it caused a lot of issues when you had databases that were handling both types of workloads, but were not necessarily designed or configured for it. And so that's where we started to look at breaking the data warehouse off from the transaction system. It really, because the nature of transaction systems is the load's is usually relatively constant, whereas data warehouse, basically queries, can really have sharp spikes. And this was at the time based on relational data. That was really what we knew, and at the time it's what we needed, because this is at the time the opening of the internet, so we started to have a lot of transaction type data. What we didn't have at that time is we didn't have all the devices, all the social networks, and machine data that we have today. So at the time, going to a relational model was really quite adequate. I recall basically looking at I still have it down in my notes. This is back in I think it was 1997 that the largest data warehouse was a data warehouse of the size of about 700 megabytes. It's kind of comical to look at that, but at the time that was thought to be a lot of data. But it basically gives you an idea that at the time it was a fairly contained problem, but we were starting to deal with issues, say, like data quality. But again, relational was perfectly adequate at the time. You're dealing with data where you're basically, coming from your internal sources, whether they be, financial back office systems, HR systems, project systems, operational systems. This stuff actually pretty neatly fit into that into data warehouses. It's a different story today. Can we go to the next slide? So, what data warehouses were at the time, designed to answer were essentially what I think today would be considered to be baseline questions. At the time, transaction systems could give you reports. You could run reports off them, and you could get reports on the gross numbers of things that have happened. Data warehouses could start to give so those systems could tell you what happened, but they didn't necessarily tell you how it happened or why it happened. So looking at the transaction system, you could not necessarily find out who are your most profitable customers. That's what you need a data warehouse for. In a data warehouse, you could slice and dice your data to get these different views and really look at them and look at the data in new ways. So you can segment out to look at profitability, loyalty. You can do the same thing with products. And so the result was that with data warehousing, you really saw not that customer segmentation was a new discipline, but it really aided it. I had a friend of mine that I've known for a number of years who at that time went to what they call database marketing. It was because of using data warehouses, and he found his home in basically doing lots of customer segmentation. We did a lot of that back in the 90s. We still do a lot of it more today, but as you can see, the world is a lot more complicated. Can we go to the next slide? Another, this looks at just an example of some of the operational questions. And again, I'm using sort of a similar model, let's say like a store or a manufacturer, to look at what it took to operate supply chains. And again, data warehouses were great for basically answering questions like who are your most reliable suppliers, who are the ones who are basically the most economical, and then also looking at the logistics side, what have been proven to be the most efficient shipping lanes, and shipping lanes being a matter, being a question of basically of, where we put warehouses, what mode of shipment do we use? Which logistics providers do we use? And to what distribution centers do we ship to? And also finding out, you could do basically answers about where most of the bottlenecks happen. Now, keep in mind the fact that when we were using data warehouses, these were batch systems that largely relied on historical data. So you would use the past to essentially diagnose the present and maybe take some very rough guesses at the future. Can we go to the next slide? The challenge, of course, and I think this is probably second nature to probably most everybody on this call, is that the data universe has obviously grown. I mean, we spoke about relational wall gardens back in the 20th century, and even around the turn of millennium. But in the meantime, we just had this perfect storm happen, basically with bandwidth, with data, and with ways that we interact. And so, for instance, messaging, which at the time was email, today there's like text messages. There are all sorts of different sort of instant messaging apps. We also have there's lots of text data out there, a lot of logs from connected machines, and that leads to, let's say, the Internet of Things. There's also a lot of location geospatial data, and that really exploded, not only with GPS systems, but also with GPS-equipped smartphones. So this has really expanded the envelope. And the result is that we've seen the emergence. We still use data warehouses. There's no question about that. They still are very important for for answering those baseline questions. They're increasingly being supplemented by data lakes. But what we're finding is that in a data lake where you put all this stuff, there are going to be certain types of problems that using a data lake, it's not going to be the most efficient answer for. And so this is where, can we go on to the next slide here? So I was giving that reference to the perfect storm. And amongst the things that have happened, I'm calling this the perfect storm plus more, because the perfect storm is basically three things coming together. It's more than three things coming together. We've had the emergence of the cloud. And yes, if you really want to get deeply historical, we've always had it. Just we used to call it time sharing. But Amazon really changed the rules when they basically realized back in 2006 that we have all this compute capacity, and they actually realized they developed an expertise in supporting their business of building data centers. So let's rent out some of this stuff, and developers started to use this to say, let's say we can do test and development there, do sandboxes there. It was made a lot of sense. Basically, didn't have to go and buy machines that you had to use, occasionally. And then we started to see, expand through use of what I'll call opportunistic, applications. So new apps that were basically born in the cloud, like for instance, like mobile apps. And that leads to the next thing, which is we saw smart mobile, which basically exploded not only the amount of data, but also the degree and detail of data that we can get on basically on customers, or we can get on things. And bandwidth in turn has multiplied. It's a matter of debate in terms of whether it's kept with demand or whether demand is overwhelming bandwidth. I know here in our house last night, we basically, in our home office, I was doing a live panel session while my wife was doing a remote Zoom session, and it handled it pretty well. Also, our storage options have multiplied. We have different, form factors of disk, whether it be fast disk or whether it be dense disk, but we've also had, basically as flash has become more reliable, flash has become a new de facto standard for transaction systems. Also, declining costs of memory, and now also persistent memory. And so you've had a multitude of options for how we can accommodate this data. It means that we can keep a lot more of this data, and we can keep a lot more of it live and accessible. And in turn, that's been supplemented by the fact there's just been a huge explosion of data. There have been lots of estimates that say that that things that the volume of data is doubling every 2 or 3 years. I don't doubt that. Can we go on to the next slide? So what it means is that having all this data can be both, both a blessing, and a curse. It's a blessing in terms of there's a lot more stuff you can find out. It's a curse in terms of trying to figure out, well, how do we handle this data? How can we query this data? Data warehouses which relied on the walled gardens of enterprise transaction data that was very, very well defined and very, and its structure was well defined. Well, that doesn't really apply in this new world of data from anything and everything. And in turn, basically, customers used to just interact with you, basically, either through the phone or they went to a store or to a website. And today, it's like, even if they're not directly interacting with you, they may be talking about you. They may be listening to other people about you on social networks. There may be basically also, by virtue of the GPS sensors in your mobile phone, your locations can be tracked. And when you go into a store, there are beacons that can detect, where customers are. And in some cases, if customers are members of loyalty programs, who those customers are. And in fact, you're taking a look at all the new generation of Amazon smart stores, and that's exactly what they're based on. No registers. They know who walks in the store, and whoever walks in the store just takes the merchandise and walks out. Nothing is done. It's all recorded. It's all tracked through electronic sensors. And so therefore, finding out who it's easy to find out what your best-selling products are, but answer the question in terms of why. For instance, what things happened? What did people say? What were there special conditions like what's happening now with basically with stay in place, where when we go out to stores, our buying patterns different. We went out to Trader Joe's last weekend and spent about $500, which is probably about 3 or 4 times what we normally spend, and we bought things we didn't normally buy. Well, there were some special circumstances there. And under these conditions, we're in very special conditions right now, or very unusual conditions right now. Why are your best suppliers today reliable? There are going to be a lot of different factors that go beyond basically the way they set up their business. It may be in terms of, what's the health of their workers, what's the quality of their health plan. So a lot of different things that come into play, which a lot of questions that you're not going to be able to necessarily easily answer through a conventional data warehouse. Can we go to the next slide? So what I'm kind of leading up to is that on one hand, we've always been connected. It's just that we've never been as connected as we are now. People have always been, unless you're an orphan, you've always had a family. Hopefully you've always had circles of friends. And if you're employed, there are people that you associate, through your professional life. So you're connected in all these different groupings or tribes. But in turn, basically, things happen in the real world. They don't happen in isolation. There's a confluence of events. I go to the store. I get in my car. The roads are either congested or they're not. There are parking spaces or they're not. It's just a very simple example. And so basically, events both connect and disconnect people, and events themselves are interrelated. Because for me to get into the store, I had to get into a car. And I had to have basically a functioning transportation system. Things in turn are connected, and they're connected as never before now that we have basically smart connected sensors on so many things. It's the Internet of Things. Places are connected. We've connected them early with transportation systems. They're now connected also with communications, and basically a quality of connection is defined often by the degree of bandwidth that they have. And that places that have very poor bandwidth are a lot less connected, and it drives the types of economic activities that happen there. So that's a key factor. And of course, the processes are connected. Can we go on to the next slide? So the thing is that what I'm trying to get to is that if you're trying to answer a question of why a customer is loyal, in the past we could look at it just from a very cut and dry standpoint, from a transactional standpoint. Do we offer the right products? Do we offer the right at the right price? And today what you see is that it's a much more complicated environment out there. As I said, events rarely happen in isolation. And the thing is that with this, as I mentioned before, we've had relational databases, data warehouses, and they're very useful. We've also had data lakes for basically starting to do exploratory analysis. But these types of data platforms alone really cannot are not very efficient at discovering how relationships, the connectedness of things, really drives this. That's what graph databases do. They represent, basically, the complex interrelationships that are the real world. I mean, you see here basically a slide based on, this is based on a long-standing heart study that's been conducted, the Framingham Heart Study. I think it's been conducted for 50 years or 75 years, something like that. And this, in this graph, which looks almost like kind of a piece of art, or this diagram, it shows basically, it shows you basically connections and qualifies data by gender and by basically their part, their activity. This basically being intake into the health system, and in turn it shows the connectedness in terms of whether it be through your friends or family. Connections basically can answer a lot of things about epidemiology here. It can answer questions here in terms of why are certain people more prone to coronary episodes than others, and how that may have happened. For instance, what type of, what groups of people, what were their families like? What types of diets did their families have? What type of healthcare did that family have? It can basically talk about if events and results are related. A great example of that, and I just read this today in ZDNet, which is a place where I basically do a weekly post. It was a post by one of my colleagues up there that that's discussed results of a study on coronavirus, on COVID-19, just conducted by Google researchers that analyzed basically the patterns in the pandemic. And what they found was that the traditional patterns with infectious diseases, these traditional assumptions, which is someone gets infected, passes on to one or two people, that model is broken down with the coronavirus. And what they're finding is that the more probable vector has been basically through clusters and through people who are super carriers, kind of like another look at typhoid Mary. And their recommendation, and the way they analyzed this was using a graph approach. Their recommendation was basically for targeted testing and contact tracing. But that's a prime example of a classic graph analytics problem, trying to just trace this pandemic. So now that I've given you a little bit of the background, I'd like to turn this over to Victor, who can really give you some deep dives into some actual use cases with some TigerGraph customers.
Thanks, Tony. So here are some of the use cases that we see, right? We have new use cases come up all the time, but these are some of the most common ones that we see with our customers, right? So right off the bat, entity resolution, the idea of, you have different users that are represented as different personas in your use case, whether it's different patients, different users, different customers, and to be able to resolve that into a single entity and then use that big picture to kind of do recommendations. That's entity resolution. I see that as a foundational use case for TigerGraph, and that leads on to other things like anti-fraud and anti-money laundering, as well as things like Customers 360 and recommendations engine, and TigerGraph being able to go very deep in terms of the analytics, and I'll come to that in a little bit. It makes us ideal for feature generation for machine learning, and of course, cybersecurity and supply chain, as Tony has alluded to before. Okay, so let's look at the first use case, which I will demo, which is fraud and anti-money laundering. Right. Let's look at why TigerGraph is a great fit for this. So to analyze fraud effectively, right, you oftentimes, you need to do very deep link analytics, 6+ hops, not just that, but, sometimes going as deep as 10+ hops, right? If you look at the idea of a hop being the equivalent of a join, right, a 10+ hop would mean you need to do a 10 join query, right? That's, as some of you know, it's going to be pretty fierce and pretty intense for a relational database to come back in a expedient amount of time, right? So to do 10+ hops, we call this deep link analytics. And it's something that TigerGraph does very well. And we can do that because by nature of our architecture, we are basically an MPP, massively parallel processing architecture. We have customers right now in production that are doing 12+ hops in the analytics, right? So in my upcoming demo, shortly, I will actually show you a sample 12-hop query, okay? The second thing that's important is the ability to go wide, right? By that we mean you need to be able to connect data sets oftentimes from multiple sources, whether it's internal or external, right? For example, we have open corporates, and we'll actually show one with healthcare later on called the FARAS database, right? You can merge these things together to go kind of wide, not just deep, but wide across a lot of data, right? Lastly, what's ideal for fraud specifically is you want to be able to detect fraud as soon as possible, as close to real time as possible. This means what you want ideally is a graph platform, a graph database platform that can analyze transactional data as soon as possible for potential fraud, right? This is something that Tiger Graph is good at too. It's fully ACID compliant. Tiger Graph is ACID compliant, and coupled with the ability to do deep link multi-hop analytics, you can essentially analyze transactional data in real time as they stream into the platform. So that's one of the things that's unique about Tiger Graph is our ability to, on a single platform, allowing you to do both OLTP and OLAP at scale. So before we go to the demo, okay, so let's go straight to the demo. The first demo is fraud detection, and I'm going to do this based off of our test drive. If you go to this URL here, testdrive.tigergraph.com, you essentially have like a set of like 6 use cases, right? One of them is anti-fraud, there's also social graph, and in every one of these use cases, there's a nice little video that showcase it, and then when you're ready, you just click try it, and it will open up a new tab. Great. This is Graph Studio, right? This is where this is the front end, web front end to the back end database. Everything I do here, there's a corresponding, command line interface as well. But very nice thing about this is you can use it to design a schema, create a loading job, actually press a button and load up the data, and then do ad hoc exploration, right? So before I do that, let's go ahead and look at the schema. Okay, so this is a social graph, okay? And I'm going to show how you can use something like this, which clearly, has data coming in from multiple places, right? So you have users, citizens, and you essentially know a lot about these people, the phone numbers that they have, and all the phone calls for each of those phone numbers, all the bank accounts, and for each bank account, all the money transfers between them, and as well as things like whether they live, hotel rooms, basically their travel information as well, right? So here on this tab called Map Data to Graph. So one of the things to consider when you are pulling in data from a data lake or data warehouse is, how is it going to come in, right? So Tiger Graph provides a rich set of what we call data connectors to help you, bring data from your data warehouse or data lakes into Tiger Graph, depending on where the data is coming in from and depending on how often you need it to be loaded. You can consider one of our many connectors. That includes a Kafka connector. We also have a Spark connector, a JDBC connector, as well as S3, right? So let's say if you have a streaming workload, right, then you would want to use something like a Kafka connector where you can define a loading job that runs continuously. For data lakes, you can consider using our Spark connector. You can read Parquet, you can read CSV, you can read into a data frame, and it triggers a loading job. We also have a JDBC connector that you can obviously use to pull in data from a relational data source, right? Last but not least, we also have a S3 connector that you can use to pull in, something like a CSV file or JSON file from your S3 bucket. So multiple ways for you to leverage your existing data warehouse and data lakes and bring that data in for more advanced analytics using Graph. Okay, so in this case, in this demo, we already have data loaded in, just CSV files, right? So what you do is you essentially drop a CSV in here, and then you tell us how, drag and drop, you say this column is going to map to this attribute, right? So the idea of a table kind of maps to the idea of a vertex type in in the graph database. And you would do the same thing. You would do the same thing for relationships, right? So I am using this file here, bank transfer records.csv, and I'm using it to map the money transfer between a bank account and a bank transfer event, right? So you can see that there's something called G-SQL concatenation, right? So what this is an ETL capability, right? What it does in this case is it merges 3 columns and then have that output go into an attribute, right? This is a test drive, which is already pre-built demos. It's read only. You won't be able to do, all these things are grayed out. Let me just go to another instance here where I can show you the sort of ETL functionality that's available. Okay. Anyway, you have ETL capability to do things like trimming white spaces, right? Trimming white spaces, uppercasing things, lowercasing things, changing things to an int, down to things like regex, right? Regex, match and replace, right? So a lot of functionality in terms of ETL that you can consider using as you bring data into the platform. Okay, so back to my my demo here. So this is a fraud demo. I'm going to show you. Let's say you have a citizen that's a known bad actor, right? So 271. I'm just going to come in here and say, give me the full name. So I know Wayne Shaw, and you can tap on this little thing here to give me more real estate. Hang on a second. Okay, that's not what I wanted. Hang on. Explore graph. Okay, so I have 2 people here. Again, I'm gonna just show the full name. Right, so let's say one is, I'm conducting an investigation, right? Let's say 271 is somebody I know is a bad actor, there's some fraudulent historical background in fraudulent activity. And then I'm right now investigating citizen number 273, Callie Turner. And I have a suspicion this person is, up to no good. I just can't quite put my finger on it, right? So this is a classic case of, you got 2 vertices. Is there a way you can connect? Is there a connection between these 2, right? To do this, a very classical algorithm that you can use to do this sort of thing is called shortest path, right? I think everybody with any kind of computer studies background at all understands what a shortest path algorithm. It's basically 2 nodes. Can you connect the dots, right? It's probably the most well-known graph algorithm out there. With shortest path, you need to also give us, how deep you want to go, right? So the way you do this, it's such a common algorithm. We have it baked in the Graph Studio. There are a whole bunch of other algorithms that you can use, but let's just go ahead and populate the source and the target, right? So the source and the target, and I'm going to hit find paths. Find me a path, within 6 hops, right? There's nothing there. So let's go up. 8, no connection at 8. I'm just going up in increments of 2, right? So finally at 10, I can change the layout here. And you can count it out, 1, 2, 3, 4, 5, 6. So we managed to find a link between them, right? So this is 271 and there's 273. What we found is essentially it's a phone number that's part of a phone call. It's part of another, part of a phone call that's to another phone number that's, a slew of phone calls. So suspicious activity, right? Suspicious activity, there is a link, right? So let's say I wanna go into the next one step higher to see if I can detect any kind of money transfer between the 2. Okay, now to do that, what I can do is I can use the shortest path algorithm again, but kind of fine tune it a little bit more, right? So first, let's go to the schema again. So what I just did, the query I just did, right? I gave it 2 citizens and I say connect dots. It's going to consider any combination of these other vertices. We found one where, you know, the citizen has one phone number that calls another phone number that calls, you know, we found this one here. But if I'm looking for money transfer, I'm looking for like, you know, money laundering potential, right? What I'm interested in is these 3 nodes here, right? Citizen has bank account. That's part of a bank transfer that goes to another bank account that belongs to another citizen. Can I establish money laundering potential, right? So to do that, I can utilize the same algorithm, shortest path, but limit that to just these 3 vertices and these 2 edge types, money transfer and bank account own. Okay, so let me go back here. Right, so instead of looking at all vertex types, I'm only interested in citizens. I'm interested in bank transfers and bank accounts, okay? And likewise for edge types, I'm only interested in bank account own and money transfers, okay? So now I'm gonna, you know, doing the same exercise, but limit the shortest path to only those vertices and edges that I'm interested in. So find a shortest path at 10, nothing. See any money transfers at 12. Still nothing. I'm just going to go up by increments of 2. And there you go. We found a link. Let me redraw this a little bit to show it. So this was the original shortest path where there's, you know, each person calls another person, and, you know, and this is the new one, and you can count it out. It's 14, right? Now, think about how you can do shortest path in a relational database or data warehouse. It's not something a SQL database can do for you. It's not, you know, in all fairness, it's not something they thought about when they developed relational databases 30 years ago. But with a graph database, right, it's something we can do very easily. Okay, so you can just trace it out. 271 has a bank account that's part of a bank transfer to another bank account, and you know, there is a money trail. Okay, now this is the explore graph where you are essentially, you know, you have a hunch, you try this, you try that, and then you find something, right? Now, if you have a particular pattern that you are repeating over and over again, then you can consider using GSQL to write what we call, you know, the equivalent of a store procedure, essentially, for your graph database, right? So connection mining takes the same thing, citizen 1, citizen 2, and the depth, right? So we can run this. 3. Okay, so before I go into the results here, right, I just wanted to show one thing, right? In the load data, in the social graph, this is where you actually load up the data. I just want to show the size of it, right? It's 1.2, about 1.2 billion vertices and 2.3 billion edges, right? So a total of 3.5 billion nodes and edges. Not terribly big, but not small, right? And you can see the breakdown there. It's like 10 million home addresses, about 40 million citizens, 400 million bank transfers, 20 million phone numbers, and 600 million phone calls, okay? So the results that you see here, okay, of the query that we just ran, it came back in split second across like 3.5 billion nodes and edges, right? So again, if you step back and think how you can do this in a relational database, the answer would be not very easily, if at all possible, right? And certainly not in sub-second response times that you just saw, right? Milliseconds, okay? I think we have some questions.
We have a few questions. Do you want to
Okay.
handle those now?
We could, yeah. Does the data from S3 get copied into Tiger Graph database, or does Tiger Graph reach out to S3 as needed? it gets copied into Tiger Graph. Okay, trying to understand. Okay, great question. We'll answer it online. Anil Verma. Okay, hi Anil. How many simultaneous queries can Tiger Graph run at the same time? It depends on how you configure it, right? You can certainly do a cluster of these machines. And the more machines, the higher the QPS that you can handle, right? So we had a use case where we loaded up about 6.6 terabytes of data in 4.5 hours using 4 machines. And each of those machines had like 128 GB RAM, giving a about how many 10 milliseconds per query. That's on average 11 hops, and they were able to get like 2,300 QPS queries per second. Okay, thanks, Anil. Okay, so any questions? Tony, anything you want to add?
Well, I mean, put it this way, this is very basic, but I think one thing a point that you really picked up on is that to do these types of queries in a relational database is just, I mean, not designed for that. I mean, relational database, you'd have to basically do almost a scary number of joins to the point where it's just not doable. And I think just in terms of where you're looking at trying to uncover fraud, the fact is fraud by its very nature today, unless you're dealing with, let's say, people who are basically players in Ozark, for those of you Netflix fans out there. But for anyone more sophisticated than that, chances are these fraud, the fraud is going to be set up to a fairly complicated chain. The idea is to elude detection. And so therefore, what you found, I mean, what just kind of blew my mind was that, first of all, just in terms of phone contacts, it had to go through a series of about 10. It probably went through a bunch of burner phones in the process. And then looking at the money trail, again, the way basically you have basically assets that are hidden under other assets, you had to go through 14 hops. And this is basically what a graph database is just as a forensic tool is just invaluable. Now apply that now to basically tracking down, as I was mentioning earlier, the COVID pandemic. I mean, that's a huge graph problem for which we do not have adequate data for many reasons. Don't get me going on that, but the thing is that as we can put together the data, as we can get more testing, hopefully, and as we can get contact tracing, this becomes a classic graph analysis, and hopefully there will be some more controlled sort of trials, in coming months as we're starting to get, as we start to, learn more about this beast. So basically, what you're showing here, just from fraud analysis, was just a very powerful sort of example of basically how graph can be, in this case, an incredible forensic tool.
Yeah. So we could easily trace one of these guys, but it's crazy. I call this a big brother demo, big brother on big data, right? So yeah. I mean, just to show how crazy this can be, we track people are connected from having the same hotel room stays, and then they want to transfer money, and then phone calls, any myriad number of combinations of the two, right? So
I mean, put this one: when you look at procedural crime shows, you see basically, essentially, investigators doing this manually. They basically have notepads, and they kind of chat. This one contacted that one, who contacted that one. Having this is just, I mean, it doesn't replace basically, classic, legwork, but it certainly gives you a leg up when you're doing that legwork.
We have a question from Thomas Haig. When trying to understand historical connections or events that have taken place over a certain period of time, you don't know what you don't know. What is the biggest challenge you face in terms of the adoption of Tiger Graph or GraphDBs? Very good question. Essentially, we're still in the early days of a graph database. I know there's a lot of organizations out there that have already adopted it wholesale. I've gone to it for extra, competitive advantage, but there's still a lot of people who don't know very much about graph databases, and that's what these webinars are about, is to kind of put the word out and educate people as to what's possible.
Yeah. Can I just
Thanks.
step in there, which is that, you know, and I've been tracking databases for too long. And I remember basically after Y2K, it was kind of felt like almost you could, you know, the conventional wisdom was close the patent office, relational databases are the end state. And so there's always a, you know, today, of course, we've had, you know, explosion of different database types. And of course, there's always the question of, does the world need another new database? When you take a look at the types of problems that graph solves, it's just a powerful sort of statement in terms of why we need, you know, at least this, you know, we need this type of tool. We need this type of technology. I think that basically that, you know, to me, graph databases, I think when you explain the logical use case, which is that the world is basically a huge graph, you know, it's connected. When you explain the connectivity, you know, the use cases become intuitive. I think at that point, that's basically, you know, in order, you know, let's say if you're, you know, within your own organization, and you're going, let's say, to your, you know, to your bosses, the folks that basically write the checks, is that they'll likely be, you know, I mean, they may be skeptical about, do we need another new fancy piece of technology? Well, you know, describe this really in terms of the problem that the type of problem that it solves. When you explain it that way, it becomes incredibly intuitive.
Mm-hmm, mm-hmm. Yeah. So interest of time, right? I'm just gonna.
So Victor, in the interest of time, we do want to make this webinar as informative or as interactive as possible. And
Sure.
there have been a few additional questions that came through the Q&A
Mm-hmm.
tab.
Mm-hmm.
I'm not sure if you've been able to see those, but one question is, do you use data from multiple banks? If so, how do you address data privacy concerns?
Yeah, so obviously you need access to that, right? We're talking to clients that can't name them, but they're in the related to the payments industry side of things, and it's not Visa, right? They have access to what's available from different accounts, right? So for a certain user, if you already have a mortgage application, sorry, not mortgage, you already have a mortgage with Wells Fargo, they can also see that you already also have an account with Citibank, so they can tell Citibank that don't bother offering another mortgage to these guys unless you can beat the rate, because they already have one with Wells Fargo. Why not you focus on credit cards and that sort of thing? So yeah, there are vendors, there are customers out there that have access to Uber data.
Okay.
Right? Yeah. So
right. Another question. Sorry, there's quite a few. I just wanted to touch on those real fast. Next one is, how would you go about using real-time JSON data source that varies from one JSON file to another with thousands of keys, many nested levels and arrays? Would you have to manually map the data to fields when loaded to make it useful? Or can you leave it in a giant JSON blob and still run analytics on it?
yeah, so we can ingest JSON as well. You know, you can also use Kafka, our Kafka connector that can stream in these data. It's a question of putting some complexity into the Kafka connector. This is a very good question. It's a big question. If you're interested, we can set up a separate time and kind of drill in further, one-on-one. Okay.
Perfect. Another question before we go to the next demo. Can you speak a bit about property versus RDF graphs?
Sure. So an RDF graph is, you know, a triple store, right? They are very different from a label property graph. A label property graph, depending on what you choose, can be made to ingest RDF data, triple store data. But you have however, you need to have a different approach, right? You need to create a generic schema that can fit this, you know, any kind of subject, predicate, object, triple store data that can come in, right? And we actually have a webinar that we've done previously. It's called Graph Gurus. Graph Gurus episode number 1, where we kind of go through the whole process of here's how you can create a schema in a label property graph that can ingest this triple store data, right? So it's a label property graph can store RDF data, but it's a generic schema that you have to come up with, right? We're not native RDF, if that makes sense.
Okay, cool. One other question. When you identify fraud rings or paths of transactions, are you considering time ordering of the transactions in the paths and loops?
Yeah, so in this case, we are not, because that's just not there's no time component of it, but there's nothing to stop you from adding a time component, right? That's the whole idea behind a label property graph. It's a lot of flexibility. You're no longer straitjacketed by a third, fourth normal form in your OLTP SQL database, or a star schema for that matter, in a data warehouse, right? You can model things as you see fit, right? So if you want to have some kind of time analytics, time series analytics, you just add another vertex, whatever granularity you want as far as time is concerned. Just represent that time component in your graph, and then hook it up to any of these other vertices that you want to time analyze. It's kind of very high level, but in a nutshell, yes.
Okay, sounds good. Great, thank you.
Okay. Shall we go on to the next one? So the next one I'm going to show, I don't think we have time to hit all three, but I'll quickly show customer 360. So what our customer 360 is essentially an example of bringing data in from a relational database, right? In this case, if you're familiar with Salesforce, right, you should be familiar with this schema, right? It's just one-for-one, something we spit out from a CSV file. From somebody's Salesforce instance, we obfuscate the data, obviously, but just kind of briefly, everything comes into Salesforce as a lead, right? A lead gets converted after some time of engagement. You talk to a salesperson, you think it's an opportunity, it gets converted to a contact. The contact's part of an opportunity. Its contact also belongs to an account. Account has multiple opportunities, and this particular demo shows how you can, attribute, right? So you have opportunities that close, right? From a marketing perspective, right? What type of campaigns did the participants in this opportunity, what were they consuming before they decided to pull the trigger and write you a check, right? So from a marketing department perspective, it's very useful to say, oh, okay, this particular campaigns was useful here, these ones not so much, right? So a campaign, this campaign member table here, vertex, is essentially a many-to-many relationship, right? So clearly the marketing department is going to fight campaigns. Each campaign goes to multiple contacts. Each contact or lead obviously is going to consume multiple campaigns, right? And the campaign could be download this white paper, sign up for this data warehousing webinar, right? It will show you how you can move data from your data warehouse, data lake into a graph database and do graph analytics. So just a little bit about the schema. I'm not going to go much more into the map data, but yes. Okay, cool. So what I wanted to show is essentially another graph algorithm called similarity, and I'll kind of, so by default, right, if you were to double click on a vertex, right, it shows you the next one hop neighbor. Okay, so you can see here, right, this particular account called VRG Payments, this is a fictitious account, a customer that's looking for anti-fraud applications, right, using graph, right? So you can see the multiple contacts, right? It takes a village to close large accounts, right? You see, engagements with data engineers, with principal software engineers, with managers, so on and so forth, including CTO. The green ones are basically the opportunities. We have two opportunities here. One is a renewal. You can see there, and this one right here is this green one right here is it's a brand new opportunity that closed in the last 6 months, right? It's for fraud circle detection, customer 360. So I can use the same trick here, and I say, I want to probe deeper into this particular opportunity. I'll double click, and you can see the highlighted subgraph, basically all the participants in this opportunity. So I'll use this trick here to show only the selected ones. And I can come into this probing and drilling down into this particular opportunity, right? And I can see there are 3 people who participated. There's Joshua King, he's an data engineer. There's Jamie Walters. I can come in here and say, for the contact, show me the create date as well. Okay, so now I can see Sam Eisenberg on June 12th. And then Jamie Walters was created on June 21st. So now I can say the guy who's probably pivot, key pivot in this deal is the guy who signed up first, who got created first, right? I'm going to say this is the guy, Sam Eisenberg, right? So I double click on it and then come in here using the same trick, say show only selections. So then I'm delving into Sam Eisenberg's world, right? I can go on and click and say, okay, each one of these is a campaign, right? So he signed up for a free trial. If I continue to do this, I can. But what I have done is I've written a very small query to say, given a customer, just show me what are his touch points, his or her touch points, right? This is GSQL. Again, it gives you a store procedure approach to your graph consumption, graph analytics consumption, Eisenberg. And you can just, this is also available in our cloud starter kit. So I click on here. So the subgraph shows up, okay? Subgraph shows up. Now you run this in Graph Studio, this nice little, it can tell you, he signed up for a test drive, he did this and this and this, right? But also available for you is the JSON output, right? The JSON output. So what can you do with the JSON output? Well, first of all, any query that you write, like in this case, customer journey subgraph, is also installed as a REST endpoint on port 9000. Right, so if you call this through curl or through through a REST API call on your web application, you get all these back, right? So this just gives you the ability to kind of feed the results of your graph analytics into peripheral applications, whether it's a new UI, whether it's Tableau, Power BI, and whatnot. Okay, so here I've just gone ahead and put together a very simple HTML user interface, right? And what it is under the covers. What I want to show is, if I give you a name of a person, show me the journey. Show me the journey of Sam Eisenberg, right? So you can come in here and give it some timelines, and then you hit that. Let me change that a little bit. Okay. So here in a swim lane fashion, chronological left to right, I can see, this is Sam Eisenberg's journey, right? He first started out signing up for our through our website, the developer edition of TigerGraph. He downloaded it. He must have liked it because he's also signed up for a free trial in the enterprise edition. He then went on to sit in on a GSQL webinar, right? GSQL is TigerGraph's graph analytics programming language. He also sat in on a sales meeting with one of our SDRs who qualified him, says this is legit. Then the webinar, the GSQL webinar must be impactful because he went on and downloaded the white paper. And then he sat in on an AML webinar, secondly, and then you can see here, this is his journey, right? So a data analyst, a BI analyst, a data scientist could come in here and say, this is a very interesting journey. This everything I wanted Sam to do, he did. Okay, so the question comes up, right? So given that Sam Eisenberg is an ideal journey, right? Is there a way using Graph to find out, who other prospects are there that are on a similar journey? You can calculate that and give me the top 100 Sam Eisenberg's wannabes, right? And you can then use that list of 100 to then, use Graph again, perhaps in recommendation engine to propose next best action, right? Based on your history, compared to Sam, we recommend you download the GSQL white paper. We recommend you sit in on this AML, right? So can you do that, right? So the answer to that is yes, right? So I've written a query called similar customers, and what it is it uses a graph algorithm or an algorithm that's very good for graph. It's called Jacquard similarity, right? So essentially, all the sample input is here. Just come in, say Sam, me just copy and paste. So I want to go in and I say compare all my prospects in the database, all my contacts that have, participated in similar webinars as Sam Eisenberg and who have signed up for the same type of demos and trials as Sam Eisenberg. And I want you to give me the top 8, right? Obviously, in real life, you want to do more than 8, probably give me 8,000 or something like that. So in this case, the subgraph is not so interesting. What's interesting is the JSON output, right? So based on those things, right? So we said similar webinars, similar demo signups. So basically, demo signups and webinars, right? So give me all the other contacts that are similar to Sam with respect to these 6 items, okay? And so we come up, and with if you look at the query, again, it's using Jakarta similarity. We are ordering it by so the similarity is calculated right here, and we're actually printing it out. Right, we're printing it out. You can see it right here. Number 1 is Priyanka Patel. Number 2 is Scott Tate, and you can rank it like this, right? So basically, in a nutshell, right, you can do complex graph analytics. You can do it in GSQL. GSQL compiles into C++. C++ is the machine code, and running on top of our MPP architecture. This is about as fast as you can go. I mean, but hopefully you've seen previous demos that this is the sort of computation you can do at scale with TigerGraph, right? And you can go on to write queries for next best action. Any questions? I think there's one.
Yeah, there's another question. Well, there's a comment and there's a question. Victor, first one, I'm curious about the machine learning case usage. Can you speak to that or show anything?
Number 1, we are like 5 minutes above time. We do have a machine language demo that we can show, perhaps in another time. If you want to leave your contact with us, we can follow up. But yes, Graph is particularly well suited for machine language, especially TigerGraph, because our ability to do deep link multi-hop analytics, right? So you can use TigerGraph to generate very, very specific features, i.e. training data that you can use for your machine learning stack, perhaps in Python, and by having very, very specific and high quality graph generated features, you can increase the quality of the training data, and then, yes.
Okay, great. And then the comment is awesome demo, Victor. And I think everybody who's still with us, we have over 45 people, will agree with me that was awesome. I think, however, in the interest of time, we might just want to begin the wrap up.
Yeah, we won't have time to do the
so
opioid.
If you could just scroll forward a wee bit more. Yep. All right, great.
We won't have time to do opioids.
Sadly.
We don't have time to do opioids, yes.
Okay. And we've had another comment from Dan. Great demo! Exclamation point. And again, that really sums up, I think, all of our feelings. So thank you to everyone who's stayed on the call this long. We're 5 minutes over. We have still more than 40 people with us. Want to thank you all for joining us. If you could just head back 2 slides, Victor. One more. Yep. Yeah. So there were quite a few questions. We will reach out to all of you post-webinar and make sure that we have answered your questions completely and to your satisfaction. If you are interested in joining our developer forum, we'd love to have you join, and the URL is shown there, essentially community.tigergraph.com. Also on Thursdays, 11 till 12 Pacific time, we have our developer I'm sorry, that's office hours. I'm referring to the third point there. At 11 a.m., we have our developer office hours, which is a sort of a live chat session with one or more of our subject matter experts. And then the middle point there is you can join our developer chat, and we use Discord for that. Again, we'd love to see you interacting with us in either of those ways, or indeed all of them. Next slide, please, Victor.
Yep.
Additional resources. Victor alluded to tyGraph Cloud. That is probably the best way for you to get started with tyGraph. If anything you've seen today has piqued your interest, then we encourage you to go to tyGraph Cloud. It takes just a few minutes, about 5 minutes to sign up. It's free. And best of all, we have pre-populated tyGraph Cloud with over 20 starter kits, and those contain schema, those contain sample data. So we're basically making it easy for you to dip your toes in the water and get started with graph. Additionally, if you then wanted to change the schema, change the data, you're totally able to do that. So really no reason for you not to jump onto tyGraph Cloud immediately following this webinar and begin to learn about tyGraph and continue your journey in terms of learning about graph. We have our test drive demos. Victor used or showed one of those earlier on. There's half a dozen. We invite you to check those out. You can download a developer edition if you wanted to do so. And there's some Guru scripts, which we keep on GitHub. Next slide, please. I think people who are on the call generally are aware that we do these webinars every Wednesday, typically from 11 to 12. So please mark your calendar. They're usually of a very high quality. I think you'll agree with me, today's was an especially awesome webinar. Thanks to Tony and to Victor. Our next webinar next Wednesday, same time, 11 o'clock, is on fraud detection and prevention. Title is How Graph Databases Are Changing the Fraud Detection and Prevention Landscape for Financial Institutions. That promises to be very interesting and encourage you to attend. Next slide. That brings us to the very end. Thank you for your comment, Usha. I'm glad you found this to be useful. We hope that everybody who's spent the last almost 70 minutes with us has found this to be informative. We know you had many other things to do. You could have spent the last hour in many different ways, and we're flattered, as always, flattered that you've chosen to spend the 70 minutes with us. Thank you very much. We had a lot of questions. We weren't able to get through all the demos, but hopefully you found this to be a good use of your time. I'd like to thank Tony Bayer for joining us today. That was an excellent introduction and overview. One thing that we need to highlight is Tony has written a white paper called Closing the Analytics Loop, How Graph Databases Complement Your Data Warehouse. That was the genesis for this webinar, and we'll include a link to that in the email we send post-webinar. So that brings us to the end of today's webinar. Thank you for joining us. Hope you found it informative, and stay safe until next week.
Thanks, guys. Have a great day.